Uh,
Okay,
Okay, good morning. Sorry.
welcome. Please, the floor is yours.
Yeah. Morning, afternoon, and evening for friends from different time zones. My name is Xuewen. I'm from Fudan University, and today I'm very glad to present a paper with Im Lim Liu on the limit theory for mildly explosive time series when the initialization is in the infinite past. Uh, in this paper, we're going to present to you the model and then some theoretical results, then the extensions, and then simulations and applications. For the mildly explosive model, a lot of time series have been discussing these models. So a standard ME AR1 model is very simple, but the rho t here we model as a parameter that depends not only so it varies with t, but the rate that the rho t goes to one is some order uh, that we use kt, but so kt goes to infinity, but kt is slower than t, and this is a very influential framework that were proposed by Phillips and McDonald's. And starting from there, a bunch of papers that have been studied and extended this standard mildly explosive model. Um, well, if you set up the explosive model in this way, then the PM proves that the OLS estimator follows a Cauchy distribution. And then we can build the confidence interval for the AR1 parameter using the Cauchy limit theorem. But it requires that the initial condition has a upper bound that it must be slower than kt to the power of 1/2. But in practice, since this is an explosive model and it is very useful for modeling financial bubbles, in practice, financial bubbles often follow a long non-explosive periods. For instance, from 1995 to 2001, we have the Nasdaq dot-com bubble. So before that bubble period, it was actually followed by 22 years non-explosive period. So we would expect that actually the initial condition is much larger than the assumption that PM needs for estimation. To be more specific, we actually there are actually two common scenarios that uh, are very that in the real practice. So first one is the bubble model. So we before we have the bubble period, we actually we were in the non-explosive time period, and this non-explosive period is often modeled as a unit root progress. So so YT actually switched from the unit root to mildly explosive at some time point. And the second scenario is sometimes we are uncertain about the initial point if we use the data from K2, not K1. So suppose K2 is bigger than K1, then we would know that because the real time point ME process starting from K1 and then from K1 to K2, it is actually an ME process. And then your initial condition when T equals K2 is actually larger than KT to the power of 1/2. So both of the two scenarios will lead to non-negligible initial conditions. Uh, Here is a graph that shows you the period from the 1973 to 2020. As you can see, at the end of the beginning, from 1995 to 2000, and this period is an explosive period. But before that, there's actually a long time of unit root process. So the ratio is 5.7 years explosive versus 22 years, non-explosive. So in this paper, we want to answer certain questions such as if the initial condition is not negligible, then will the Cauchy limit theorem still work? If it doesn't work, what's the impact? And if it doesn't work, can we provide a robust inferential methods that can that is robust to initialization? And the key insight, the key finding in our paper is the initialization matters. And so the Cauchy confidence interval will fail under more realistic empirical settings. And the solution we provide here is to use t-statistic. Well, to incorporate the intercept. So in our model, we have not only the rho t part, the ME process, but we also have an intercept part. And this intercept can also be depending on the time t. Uh, so to fix ideas, let's first focus on the IID process, and then we can extend to the weak dependence assumption. So before we move to the theory, so we first want to analyze the limiting behavior of some quantities, especially things related to YT. So here we introduce two assumptions. Uh, so these assumptions is about the initial condition. The first one is from a structural break model. So before we have the ME process, we have the unit root process at first. So the Y0T is like this. And the second one is the initial condition follows an ME process. So we have Y0T follows like this. So both of these two formulas are actually from the formula itself if we go back to HT. So following the literature, we define three past scenarios. The first one is called recent past, so which is so the HT is very small. And second one is called distant past, so HT is proportional to KT. The third one is infinite past, so HT is much larger than KT. And then we can derive some derivations for the YT. So YT follows this. And then for uh, for the two scenarios, we can actually see that the Y0, they can be both be much greater than KT to the power of 1/2. So we use OOS in our estimation, and since this model is very simple, we have the formula for OOS estimator. So before we introduce the theorem, we have some lemmas that discuss the limiting behavior of the YT, some of the YTs and YT square and YT times UT. And since we have not only the intercept but also the initial condition, then these limiting results is more complicated, and it depends on the kappa, which is the horizon, which is the um, the infinite past or distant past, that intensity. And we have the delta. Delta is the intercept intensity. And this is also from lemma one that if we have a unitary internationalization, but we have a large drift, so the kappa goes to I'm sorry, so the drift goes to infinity. And within this lemma, we can derive the limiting behavior of the rho t OS estimator, and we can see here. So neither of these two estimators follow a Cauchy distribution. So it's very different from the PM, the original result. And it also contains nuisance parameters, delta and kappa. Now let's then discuss the limiting behavior under the ME initialization. And in this case, we have divided the limiting results into four subcases. The first case is moderate drift, and distant pass. And the second case is the large drift, but distance pass. The third case is the moderate drift, but infinite pass. And the fourth case is large drift and infinite pass. So combine all the subcases together, we can derive the following theorem that under these four cases, we have the limiting behavior of the OLS estimators. All right. And as you can see, none of these four cases give us a Cauchy limiting result. But actually, well, there's a special case that in case three, with no drift, and when delta is zero, and the in the past case is in the infinite past, we have the Cauchy distribution result, but the rate is much faster than the PM result. Okay, so to summarize, up to this point, we have derived the limiting behavior of the OS estimators in the ME model under three different classifications. Well, it is called the recent distance and infinite, and it's actually adapted from Phillips and McDonald's in 2009 econometric theory paper. So their paper focused on unity rule models. They show that in the infinite pass case, if you have a unity rule model, then your OS estimator will actually follow Cauchy limit instead of the Fuller distribution. But in our case, we show that uh, in the ME model, you don't have Cauchy, but you have something more than Cauchy, and it contains a lot of nuisance parameters. But after we work out the t statistics, we find all the complicated terms, they actually cancel out. So the t statistics will give you a standard normal result. So this is pivotal, nuisance parameter free. That is a very lucky news. And based on this t statistic, we can construct a confidence robust confidence interval. Uh, Okay, this is basically what we have done, and this is a core idea. And based on this core idea, next we're going to do three extensions. So the first extension is we extend our framework to weak dependent scenario. So in the weak dependent errors, we have to work with the long run variance estimator, and we show that if we replace the standard error with the hack standard error, we can achieve the usual standard normal inference. And in constructing the hack standard errors, we actually using this form of the hack standard error. So this is very different from the conventional hack estimator. Uh, and uh, we actually found that both of these two estimators are consistent, but the first one is preferred. So for the weak dependence, how to prove this? So we have to use a BN decomposition. And uh, so following our earlier proof, so this extension is quite straightforward. All right. Uh, and both of the two standard error estimates, they are consistent. And the second extension we deal with is exogenous regressors. So if these exogenous XTs are included in the model, and then we can again use the conventional t statistic. Uh, and at the same time, we adjust for long run variance. All right. So what are the gains of including the exogenous regressors? We can have smaller standard errors. And the third extension is
You
the
have
high
five
dimensional
minutes.
set.
You have 5 minutes, okay?
Thank you. Yeah. We have the many regressors set up. And in this setup, we have the ZT, the group of the regressors, but in ZT, there are XT, the P-relevant regressors, and the rest of the regressors are irrelevant. Uh, So the number of the irreversible regressors might be large and possibly can be greater than t. So this is a high-dimensional problem, and we propose a three-step post-lasso procedure. So firstly, we regress the AR1 regression and then get residuals. and then do a lasso over the regressive residuals on the exogenous regressors. And then after the, the model selection from the second step, we can do a third step, the post lasso least squares on the selected variables. And in our paper, we show that this three-step procedure works well. It follows a standard normal distribution. All right. Now let's look at some simulations. We have three DGPs. The first one is IID, and second one is MA. Third one is with exogenous regressors, and we have different intensity of the rho t, and we have different the HT and intercepts. All right. So the first table shows that the Cauchy confidence interval it over coverage the parameter, but our t-based confidence interval approaches 95%, which is the ideal level. And under MA errors, as you can see, now the ID t-based interval does not perform very well, but our New West confidence interval performs very well. And this is an exogenous regressor setup. While here we introduce the CLLS. This is the best performed model. So it actually uses a true XT. All right. So this least square performs the best, but the post lasso least square is actually close to the least square. All right. Now let's look at an empirical application. We analyze the data from the NASDAQ index from 1990 to 1999. We have applied three confidence intervals. So first one is Cauchy based, and second one is our t-statistic based, and third one is also our t-statistic based, but with the post-lasso selection methods. Well, as you can see from this table, that the Cauchy confidence interval it is from 0.991 to 1.059, and it actually includes 1. So this is problematic because this is a model that we have already assumed it is a model explosive model, so it shouldn't include 1, right? If Cauchy inference is accurate in this setup. And as you can see, the confidence interval is too wide. But our confidence interval t-based are narrow, and it excludes 1. All right. Well, if we did a robustness check or we did a subsample, we changed the initialization a little bit to 1991. Now you can see the Cauchy confidence interval is still very wild, and it is very sensitive from 1991 changed to 1969, right? And the low upper bound from 59 changed to 77. So it's very sensitive, but our confidence intervals remain less sensitive. So the difference is actually from the Cauchy confidence interval. It has a strong assumption. But in our t-statistic-based confidence interval, we have relaxed this assumption. All right, so this is basically what we have done. So we have provided that t-statistic. You should use that in mounted explosive autoregressions because it is robust to initial conditions. Thank you.